Alright everybody, welcome back. This is our second video on the section 6.3 of AP Calculus, Riemann Sum, Summation Notation, and Definite Integral Notation. In the last video, we developed the idea of using an infinite number or an unknown number of rectangles, n, and then letting that rise to infinity. We're going to continue, talk a little bit about some notation, and then do a few examples related to this concept. Alright, so the definite integral of a continuous function on AB, if I have a continuous function on AB and it's partitioned into n subintervals of equal length, then the definite integral is equal to the limit as n goes to infinity of the sum from 1 to infinity of this expression. This delta x, of course, goes back to here. It's the width of the rectangles. And then this is saying, hey, we need the function value somewhere in the subinterval. We're going to tend to use the right endpoint because it's the easiest, most convenient to work with as far as building models. So that's why we'll work with that. And so in general, this expression right here is the same as the definite integral. Okay? All right, here's the definite integral notation that we've seen before, and everything that's related to it. We've got the integral from a to b of f of x dx. That's how we read it. And the different component parts, the number at the bottom of the integral sign. This is the integral sign, the long stretchy s. The number at the bottom of the integral sign is what's known as the lower limit of integration. The number at the top of the integral sign is the upper limit of integration. The function that is inside this integral is what's known as the integrand. The dx here tells us that x is the variable of integration. And this whole thing is described as the integral of f from a to b. When we find the value of this, we will say that we have evaluated the integral. Now, something to point out here, the importance of the dx, because it tells us what variable we're integrating with respect to. But I've heard several people, and I've talked about this a little bit myself in the past, that this integral sign right here and this dx, they form kind of a set of grouping symbols, almost like a set of parentheses, where everything that's between the integral sign and the dx is what is your integrand. So that's another way that you can think about what's going on here with the notation. All right, now, at the very bottom of this page, this is kind of the template that we used in the last lesson, where this integral was equal to the limit as n goes to infinity of k from 1 to n. This right here was the width of the rectangle. And then we found the function value starting at the left endpoint, adding the width of the rectangle times k, and substituting that into the function to generate each successive area in the formula. Okay, this is a very, very helpful way to think about this. If you can utilize this right here as your method for writing and interpreting these Riemann sums and the summations related to them, you'll be in pretty good shape if you can interpret them in this fashion. All right, let's go ahead and we'll start working our way through a few examples. All right, example 2 from this lesson. We are going to rewrite this definite integral using summation notation, the integral from 3 to 5 of x squared plus 2 dx. Okay, so we want to turn this into summation notation. So this is going to be the limit as n goes to infinity of the sum from k equals 1 to n. That's uniform every time. And the first thing we want is the width of each rectangle, which we're going to get by taking the difference between upper limit of integration minus lower limit of integration divided by the number of rectangles. And so the width of each rectangle is going to be 2 over n. And then we're going to multiply that by the function. And again, we're going to utilize this template. Lower limit of integration, 3, plus the width of each rectangle times k. Okay, now in this problem we do have a specific function that we can utilize, the function x squared plus 2. So we're going to utilize that function and replace this piece of our summation notation to get to the way that we actually want to write this particular integral. So this is going to be the limit as n goes to infinity of the sum from k equals 1 to n of 2 over n times, and my function is x squared, so I'm going to put this expression right here in for x. So that's x squared plus 2. That was our function. And this right here is my summation notation, Riemann sum representation of this definite integral. Now, when we're given an integral, there's only one way to write it in summation notation. When we're given something in summation notation, it is possible to write this as multiple different integrals, potentially. Okay, so let's take a look at this one. First of all, I look at this and I see, okay, this is the width. And then it looks like we're starting at 2. And our function is taking whatever we put into it and cubing it. So I could write this expression as the integral from 2 to 5. I get 2 to 5 because we're taking a width of 3 and dividing it by n. Integral from 2 to 5. And then this is our starting point, our left end point. And this is our width. And our function is taking what's inside there and raising it to the third power. So there is an integral that represents that particular summation. Now there are others. In fact, there are an infinite number of others that I could write. Okay, suppose instead, maybe I think that instead my function is f of x equals 2 plus x, the quantity cubed. If that's the case, then all I've got here is this is the width, and this would be the same thing except the integral will start at 0 and go to 3. There's another representation that matches this summation. So usually if I want a specific value from you as far as one particular integral that represents this summation, I usually have to give you a starting point of where to start at. Okay? All right, the next one. The expression 1 over 12 times sine of 1 over 12 plus sine of 2 over 12, etc., is a Riemann sum approximation for what definite integral? Again, we could make some arguments that there are different answers to this, but we're going to go for the most obvious answer here. We've got 1 over 12 as our width. Seeing that we're putting 1 over 12 into the sine function first, we're thinking about this as the right endpoint of our first interval. And so our function here, it looks like our function is sine. First rectangle we put 1 over 12 in, second rectangle 2 over 12, 3 over 12, all the way up to, and now here we're talking about the starting point. It looks like our starting point is at 0. Since our width is 1/12, and this is 1/12 is 1/12 to the right of 0. And then it looks like our ending point here is at x equals 1. And so I think the most likely definite integral approximation from this Riemann sum is that this is representing the integral from 0 to 1 of sine of x dx. All right, there's my answer. And one last question. For what value of b does the integral from 3 to b of x cubed dx equal this expression? Okay, now notice again, this is the width of a rectangle. And if 4 over n is the width of the rectangle, that means that the width of the interval should be 4. Okay, now I look at this expression and I've got 3 plus 4 over nk raised to the third power. So that matches my function here in my integrand. And so it appears like this is pretty straightforward, that the value of b here is just going to be 7. Because then the integral from 3 to 7 of x cubed dx perfectly matches this summation. Okay, it's going to be really important for you folks to do as much practice as you can with these problems. And so I'm going to turn you loose to your practice problems, and we're going to do a ton of these over the next couple of days. All right, everybody, that's the end of this video and the end of the lesson for section 6.3. See you next time when we talk about section 6.4. which is the fundamental theorem of calculus and accumulation functions. That sounds important and exciting all at once. Can't wait to see you back again for section 6.4. See you then. Have a great one. Bye-bye.